Hi everybody, so this is the end of the slides for Chapter 6. We're going to be looking at this fourth quantum number. So we've already described the locations where the electrons reside as orbitals, and we've described them by size, shape, and orientation. So this is the last quantum number. It's referred to as the spin quantum number, and it's given the symbol MS. And it was in the 1920s that it was discovered that if we have two electrons in the same orbital, that they don't have exactly the same energy. So the difference between these, essentially, if I pass the two electrons through a magnetic field, what I find is that they behave differently. And so we refer to this as the spin of an electron. You can think of it like an electron is moving in spinning either clockwise or counterclockwise. So this led to the invention, essentially, of a fourth quantum number, which we refer to as the spin number. The spin quantum number has only two allowed values, either +0.5 or -0.5. When we drew the energy charts where we placed the electrons into their orbitals, we indicated the difference between these with an up arrow and a down arrow. So we've already kind of used these rules, but these are the rules that govern the placement of electrons into orbitals. So the first one is called Hund's rule of maximum multiplicity. And this says for degenerate orbitals. Now what that means, when I say it's a degenerate orbital, what that means is that they're at the same, they take the same amount of energy to get into. All right, so these are our sublevels. So all three orbitals in the 2p sublevel require the same amount of energy to get into, and so we refer to those as degenerate orbitals. So what Hund's rule says is that when I'm putting electrons into those orbitals, that it's preferable if I maximize electrons with the same spin. So this is the idea that I have to put the electrons in to those three orbitals one at a time, and then go back and pair them up. So don't pair them up until I have to. The other rule is the Pauli exclusion principle, and this basically says that you can't have two electrons in the same atom that have the same set of all four quantum numbers. What this means is I can't put two electrons in the same orbital spinning in the same direction. So again, we indicated that difference with up and down arrows, and we never put two arrows into the same orbital that were spinning the same way. So this is another Aufbau energy chart for nickel. So I would suggest you pause the video and you try and fill this in by using the rules that we've talked about. No more than two electrons in an orbital. And then start the video again and look at the answers. So we have nickel, which has 28 electrons. So that's its atomic number. I find it on the periodic table. I started at the bottom, I filled in my orbitals, and you notice that when I get to the 3D orbital, all right, so the 3D sublevel, I should call that, all right, there are 5 orbitals there. Those are degenerate orbitals. They're at the same energy level. And so I put one electron into all 5, and then I go back and I pair up the last 3. So my electron configuration, when I write it the way that we've been doing that, looks like what you see on the screen here. The 1s2, 2s2, 2p6, etc. If I want to know how many principal energy levels are being used, well, it's 4. And I know that because the largest number on the screen here is a 4. So whatever my principal energy levels, remember, are being indicated by number. I'm just grabbing my pen again. So you can see right here, the biggest number I see is a 4, so there's 4 principal energy levels being used. If I want to know how many sublevels there are, each of these lines that goes across, so that's a sublevel. That's a sublevel. So I'm basically counting these up, and I have 1, 2, 3, 4, 5, 6, 7, not 6. Apparently I counted wrong when I put that in there for you. So when I'm writing them, I'm also writing them by sublevels. So there's the 1s sublevel, the 2s sublevel, like that. All right, so there's another one on the next slide. All right, so I'm asking you to do the same thing now for arsenic, I believe it is. So see if you can go through and fill that in now. So here's my solution for arsenic. I've got a total of 33 electrons for arsenic. So I get all the way through the 3D sublevel, and then I have 3 more electrons in the 4p sublevel. Still my largest number is a 4. So I've used 4 principal energy levels, and this time I've used 8 sublevels. All right, so as long as I give you the energy chart, it's relatively easy to fill this in. You just start at the bottom and move up following those rules. The problem comes in if I want you to write an electron configuration without looking at the energy level. And so we need to remember the order, essentially, that these sublevels show up in. So in order to do that, we want to use the periodic table. So if you look at this slide of the periodic table, what we see is that the sublevels essentially follow through the periodic table. So my first 2 columns of the periodic table are referred to as the S block. So what I see here is what I would call the S block. I'm just going to grab my pen again. So these first 2 columns, this is my S block, all right? Now, this element is out of place, all right? That is helium. And helium behaves like the other elements in the periodic table below it, but it doesn't have any p orbitals because in the first energy level, there's only an S-shaped orbital. After helium, though, everything follows in order. So I go across my first row, and I would put my first 2 electrons in the 1s block. Then I would move down to the second row. I would put my next 2 electrons in the 2s block. After the 2s block, I would move across, and I would use the 2p block. Now remember, we can put a total of 6 electrons in p-shaped orbitals, and if you count across there, you'll notice that that p block is 6 elements wide. So after I finish with the 2p block, then I come down to the 3s block and move over to the 3p. I fill up the 3p, then comes the 4s. Now what happens when I get to the part of the periodic table where there's transition elements is that the elements, as they put their electrons into orbitals, D-shaped orbitals, they're always 1 energy level behind. So in my 4th row of my periodic table, instead of having the 4d orbitals, I have the 3d orbitals. So keep going across. The other problem is these 4f and 5f. So if you look at your periodic table, these actually go between the 6s and the 5d, and between the 7s and the 6d. So I would ask you to be able to write electron configurations just by looking at the periodic table and remembering this order and how it follows with the periodic table. So we'll practice doing that again. So this is just telling you different blocks on the periodic table correspond to different types of orbitals. So this is a picture of the periodic table with the outermost energy level filled in. And so there's one other thing we want to keep in mind, and that's that half-filled and completely filled sublevels are favorable energetically. What that means is it requires less electrons, or I'm sorry, less energy for an atom to have all of the orbitals in a sublevel, either full or half full. And so there's a few irregularities that occur because of that on the periodic table. So if you look at copper, so copper is Cu on the periodic table. So take a second and find copper. It's right here. All right, so if I want to write the electron configuration for copper, I would write out the electron configuration. So this is something else we haven't done either. So you notice that what we're doing here, so they're starting the electron configuration with argon. So this is called the noble gas shorthand. So you're allowed to write an electron configuration from the noble gas that precedes it just by writing the symbol for that noble gas in brackets. So basically what I'm saying when I write that brackets with the AR is it looks like argon, and then I'm showing what happens after that. So I would want to say it was 4s2, 3d9. But what happens is one of those s electrons pops up into the 3d sublevel so that both sublevels are either half filled or completely filled. Okay? This is only going to occur, the only place you really need to worry about this is between s and d orbitals. You don't need to worry about it between s and p orbitals. It just happens for the s and the d orbitals. So typically it would happen in this group, in group 11 on your periodic table, and then the other place that it happens is in group 6. Okay. So on the next slide, what I'm asking you to do is to write an electron configuration. Oops, it's not the next slide. Wait, we're going to make one more definition, then we'll practice. All right, so this is our last definition in this chapter. So we distinguish the magnetic properties of elements by something that's referred to as paramagnetism and diamagnetism. Now, this is different than what you're used to thinking of as magnetism. So magnetism that we've played with magnets and like that, that's actually called ferromagnetism. This is a very weak attraction or repulsion. It's not something that you would actually be able to feel real easily. So it's measured more than something that you would feel. Paramagnetism is a weak attraction into a magnetic field, and it occurs whenever an element has unpaired electrons. Dimagnetism is a weak repulsion, and that occurs when all of the electrons that are in the orbitals or surrounding an atom are paired up. All right, so now we're going to try a practice problem. So what I want you to do is to see if you can write the complete electron configuration for silver. All right, so it's going to ask you to do this on the next page. So flip over to your next slide and see if you can answer those questions. Feel free to start with the last noble gas. You can use that noble gas shorthand. That's always allowed. All right, and see if you can answer the rest of the questions. And so it's a little easier to see, and because I made a mistake. So when I'm writing for silver, all right, you can see that I wrote out through krypton, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Instead of writing all that, I could just replace that with Kr. And then I would write the remainder of my electron configuration as Kr 5s1, 4d10. So the temptation is to write it as 5s2, 4d9. But this is one of those places where by moving one electron from an s to a d orbital, I can half fill or completely fill all the orbitals. So silver would be paramagnetic because in the s orbital, it has an unpaired electron. In this bottom question where it's asking you to write the electron configuration by principal energy level, basically what I'm doing here is I'm lumping together everything that starts with the same number. So everything that starts with a 1, everything that starts with a 2, everything that starts with a 3. This is actually the electron configuration that's given to you on your periodic table. So right at the bottom of the periodic table, at the bottom of each element, it'll show you an electron configuration that's by principal energy level. When I ask you to write an electron configuration, especially if I say complete electron configuration, I expect you to use the SPDF kind of notation. All right. So that's the end of this chapter. There are some practice problems you should work on and then come to the office hours and we'll go over them. Take care, guys.